And catalytic converters are key parts of the exhaust treatment system. How do they function and what causes their failures?
Catalytic converters clean exhaust through chemical reactions, handling HC, CO, and NOx. Common failures include overheating, often from an engine misfire or rich mixture, or contamination from oil or leaded fuel. Secondary air injection systems inject air into the exhaust manifold or converter to oxidize HC and CO. Failures in these systems, such as a non-functioning air pump or faulty diverter valves, directly increase tailpipe emissions or can cause backfiring during deceleration.
And how exactly do you test a catalytic converter's efficiency and identify problems?
First, a rattling sound when tapped indicates loose internal components. A significant loss of power points to a restriction. To test efficiency, you can use a temperature probe. The outlet should be about 10% hotter than the inlet. A cranking CO2 test with the ignition disabled and fuel supplied should show CO2 above 12% and HC below 500 ppm. An oxygen storage test measuring O2 increase during snap throttle should be minimal. OBD2 systems also monitor converter efficiency and set DTCs if it degrades.
And finally, the evaporative emissions or EVAP system manages fuel vapors. What happens when it fails and how do you diagnose those issues?
The EVAP system captures and stores fuel vapors in a charcoal canister for later burning. If it purges vapors at idle, it can cause a rich condition or rough idle. Saturated canisters lead to rich mixtures and emissions test failures. Leaks in the system are a common cause of gasoline odors. OBD2 systems monitor purge flow and can detect small leaks setting DTCs. Diagnosis involves visual inspection, using a gas analyzer or smoke machine for leaks, and testing solenoids for proper operation. A faulty fuel tank cap is a surprisingly common cause of EVAP leak codes.
Moving to computerized engine controls, retrieving DTCs is the starting point. How does this process differ between older and newer vehicles?
On pre-OBD2 vehicles, code retrieval might involve jumpering diagnostic connector terminals and counting lamp flashes or cycling the ignition key 3 times. OBD2 vehicles, however, mandate the use of a scan tool to retrieve and clear codes, and importantly, to view freeze frame data, which captures sensor readings at the moment a fault occurred.
Once a DTC is present, what's the next step in diagnosing the problem, and why is it important to differentiate between a history and current codes?
After retrieving a DTC, the technician uses a diagnostic flowchart to determine the actual problem. It's crucial to understand the circumstances that caused the control module to set the fault. Differentiating between a history code, which is a past fault, and a current code, which is present now, is vital. Misdiagnosis can occur if you treat a history code as a current one. On OBD2 systems, you should never clear codes until the repair is confirmed to preserve that valuable freeze frame data.
What if there's a drivability or emissions problem, but no DTC is stored? That must be challenging to diagnose.
It is. For example, a faulty throttle position sensor might have a bad spot in its circuit board, causing momentary voltage drops that affect acceleration but don't fall outside the parameters for setting a code. Similarly, a small vacuum leak to a map sensor could cause it to read higher than normal, leading the computer to increase fuel delivery and emissions, but still within a range that doesn't trigger a DTC. These situations demand careful pinpoint testing and a deep understanding of normal system readings, often utilizing specialty tools like graphing multimeters or lab scopes.
These advanced diagnostic tools, scan tools, DMMs, DSOs, seem indispensable. How are they used for comprehensive testing of computerized engine control systems?
The PCM needs sensor inputs to make decisions, then send signals to actuators. Scan tools allow access to sensor data and output commands, including bidirectional testing, where you can directly control things like idle speed or disable injectors. DMMs are used for detailed circuit integrity tests, measuring available voltage, voltage drop, amperage, and resistance. DSOs are for waveform analysis of sensors and actuators, like oxygen sensors or fuel injectors, which helps identify intermittent or subtle issues.
It's a lot of technology.
When working with these sensitive electronic components, static electricity is a real concern. What precautions are necessary?
You must handle static-sensitive devices with extreme care. Always connect grounding strap from yourself to a good ground on the vehicle before installing components like a PCM. These parts are typically shipped in anti-static envelopes, which should not be opened until you're ready for installation. It's also advised not to move around unnecessarily on the vehicle seat, as this can generate static electricity.
Modern vehicles are highly interconnected. How do failures in interrelated systems like cruise control or theft deterrence create drivability or emissions problems?
Today's vehicles have multiple computers that communicate. If a signal from one system isn't received or interpreted correctly by another, it can cause output problems. Theft deterrent systems, especially aftermarket ones, can cause stalling or no-start conditions that are difficult to trace. After replacing control modules that communicate, like the PCM and a theft deterrent module, relearn procedures are often necessary. Issues in cruise or traction control can also cause surging or power loss. Electrical interference from poorly installed aftermarket accessories is another common problem. Computerized spark timing controls are critical for engine performance. How do they work, and what happens when they fail?
The ignition module receives a signal from a triggering device, like the Hall effect sensor, to fire the coils on startup. This signal is also sent to the PCM as an RPM input. The PCM then sends a computed timing signal back to the ignition module. If there's a problem in this control circuit, the engine often reverts to base ignition timing, leading to a noticeable lack of power. Incorrect sensor inputs, like a faulty coolant sensor reporting a colder than actual temperature, can cause the PCM to increase spark advance and fuel delivery, leading to increased emissions and fuel consumption.
After all this extensive diagnosis and repair, how do technicians properly verify the fix and clear any remaining DTCs?
On pre-OBD2 vehicles, you'd follow manufacturer procedures to verify the repair by operating the system and ensuring the DTC doesn't re-trigger. For OBD2 vehicles, it's crucial to first review and record any freeze frame data before clearing DTCs with a scan tool. Then you operate the vehicle under the conditions noted in the freeze frame data and monitor the status of the specific DTC until the diagnostic test associated with it runs and passes, confirming the repair.
That's a thorough breakdown of the Ase A8 engine performance task list, covering a vast array of systems and diagnostic procedures. Thank you for walking us through it.
My pleasure. Mastering these areas is essential for any technician aiming for the A8 certification.
If you found this discussion helpful, share this episode with someone else who might benefit from this information.